This lesson is going to review the concepts of the kinetic molecular theory and the gas properties and the gas laws that we study. So first you need to understand the differences between solids, liquids, and gases on a molecular level. So solids have a definite shape. Their particles are always moving, but they're not allowed to move around each other. They're just kind of stuck in one position and just kind of vibrating. So they also have definite volume because their particles are as close as they can get. You can't really squeeze them together anymore, and you can't really separate them. But they are moving. So one of the things of the kinetic molecular theory is that all particles are moving, and we can't get them to stop just yet. We're working on it. That's called absolute zero if they were able to get the particles to stop moving. For liquids, we have definite volume because they are also packed together as tightly as they can, but these can flow. So instead of just vibrating in one position, they can flow around each other, which is why they're different from solids. And then gases are very different. Gas particles are very far apart, and they move like crazy. So they move at very high speeds. The next things you need to know are the variables temperature, pressure, and volume. And what you need to know about these are the definitions, but also what they mean in your own words. And you also need to be familiar with the units that we use for these. So temperature is a measure of the average kinetic energy. Which is really a measure of the speed of the particles, how fast those particles are moving. And the two units that we use for this are Celsius, but for this chapter you're going to have to turn them into Kelvin by adding 273. So Celsius plus 273 will give you Kelvin. The next unit that we're going to talk about is pressure. And pressure has kind of a long actual definition, and instead of memorizing the long definition, I just want you to be able to understand what it means. And the way you can picture pressure is by picturing collisions with the walls of the container. So if you picture a balloon and you picture gas particles bouncing around in the balloon, the more those gas particles hit the walls of the balloon, the higher the pressure is going to be. And there are a lot of units that we use for this. We have atmospheres, which we use ATM as the unit for that. That doesn't stand for atom. We have millimeters of mercury, which is the same thing as torr. Those two are interchangeable. And we have kilopascals. Those are the three that you're going to see for this class. And then the last variable that we talked about is volume, which is the space that something takes up. The amount of space something takes up. And the two units that we use for this are milliliters and liters. But it's probably a useful conversion to know that there are 1,000 milliliters in 1 liter. That's 1,000. Fix it. 1,000 milliliters equals 1 liter. And then what we did is we used these variables to talk about several of the different gas laws. So the first one we're going to talk about is the combined gas law, which says that P1V1 over T1 equals P2 V2 over T2. So this allows us to compare these variables. And the first thing to recognize is that if you're dividing variables, think D for direct. It means it's a direct relationship. So just looking at this equation, you can say that pressure and temperature are directly related, or volume and temperature are directly related, if the third one is held constant. Also keep in mind that you might not use all of these variables. So if something is constant in the question, if they say temperature is constant or pressure is constant, then you just ignore it in this equation. So you might not use all 6 of these variables. You might only use 4 of them. And the last thing is that for this equation, you do need to put temperature in Kelvin. In the question, it will be given to you in Celsius because that's what our thermometers measure. So then you're going to need to add 273 to put it in Kelvin before you plug it into this equation. For the other 2 variables, it doesn't matter what units they're in, but they do need to match. So if pressure is in ATM for the first one and it's in mmHg for the second one, you will need to convert that before you plug it in. All right, our next equation is called the ideal gas law. Like that, sometimes called Pivnert. This one you have to be really careful with your units. So the first thing, let's talk about volume. This one has to be in liters. So if they give it to you in milliliters, you need to make sure you use that conversion to convert that into liters before you plug it in. For the red equation, it doesn't matter if it's in liters as long as it matches, but for the green equation, you do need to have that in liters. N stands for moles. And if they don't give you moles, if they give you grams, again, you need to convert that using the periodic table, set up a little fence, and convert that into moles before you plug it in. Just like the other one, temperature needs to be in Kelvin. So just add 273 to your Celsius temperature. And then for R, this is found in your reference packet. It's on the first page of your reference packet, and it's called gas constant R. And the problem is that they give you 3 different choices so that you have the correct units that you need. And so what you want to do is to make sure that your pressure and your R value, the units match. So if pressure is in ATM, then you're going to choose the R value that matches ATM. And the last equation that we did for this chapter is Dalton's law of partial pressures, which just says that you can add up the partial pressures of each gas to get the total. So if you have a balloon that contains more than one gas and they're all bouncing around, then you can just add up their pressures to get the total. And this is the one, watch for the phrase collecting a gas over water. This is the one you would use for that. And then the last thing for this chapter is that we studied 2 different graphs. So you need to be familiar with the phase diagram, which shows the different states of matter for various pressures and temperatures of one substance. So each pure substance has its own phase diagram. For instance, water has a phase diagram, carbon dioxide has a phase diagram, so each one has its own phase diagram. And there are several things you need to recognize. Solid is going to be the coldest and the highest pressure, liquid is in the middle, and gas will be over here. The point where all 3 intersect is called the triple point. If you cross over a line, it's a phase change, and you should be familiar with phase changes, so you might need to study up on those. So melting, boiling, condensation, make sure you know all those words. If I give you a point that's on a line, that would be 2 states of matter in equilibrium. So like if I had a point right here, that could be a liquid or a gas. The triple point, you could have all 3. And then if you have a point in a space, like this is just 1 state of matter, that can just be a gas. And then the 2 more things. One is the end of the liquid to gas line is called the critical point. And this is the last point where you could still have a liquid. Every temperature beyond that is so hot, the particles are moving so fast that no matter how much you push on them, you can't force them to be a liquid anymore. So it's kind of the end of the graph. And then the last thing is you want to watch out for the word normal. If it says in the question, what is the normal melting point? Or what is the normal boiling point? You need to know that normal means it's happening at standard pressure. So what you would do is go over to your y-axis and see what unit your pressure is in. Let's just say it's in ATM. Then you're going to go up to standard. So in ATM, standard is 1. So you would go up to 1, and then you follow it over to the phase change. So if we're doing melting, you would follow it over to the solid to liquid line, and then follow it straight down. And so if they're asking you for a point, they're asking you for the temperature. And so this is the normal melting point. And the last graph that we did is called a vapor pressure curve. So this one was a phase diagram. And a vapor pressure curve allows us to compare different chemicals. So we can put several chemicals onto one graph, and we can see what kind of intermolecular forces they have and how well they boil. So if I label this chemicals A, B, and C, I can ask you several things about this. So first of all, the one farthest on the right has the strongest forces of attraction. Strongest intermolecular forces, and it is the least volatile. Volatile means it evaporates easily. This one does not evaporate easily because you had to heat it a lot to make it boil. So these lines, the points on these lines are boiling points. So notice that A's boiling points are a lot cooler than C's boiling points. So you didn't have to heat A very much to break it apart. So C has the strongest forces of attraction, which means A has the weakest. and A is the most volatile. They also could ask you for the normal boiling point on this, which is similar to what we just did. So normal means it's happening at standard pressure. So you would need to see what units your pressure is in, go up to the line, go up to the y-axis where it is standard, and then follow it over to the chemical they're talking about, and then follow it down to see what the temperature is. And that is it for KMT and gases.